In the stillness of an early morning in 1964, the ground beneath Anchorage, Alaska, groaned violently. Without warning, the entire city lurched. Streets cracked open. Buildings collapsed. Rivers reversed. And in mere minutes, the world had changed. What followed was one of the most powerful earthquakes ever recorded in North America, measuring 9.2 on the Richter scale. But it wasn't just the magnitude that stunned scientists, it was what came after. Reports of glowing skies. Magnetic field disruptions. And a series of aftershocks that didn't behave like anything researchers had seen before. This is not a story about just any earthquake. It's about those seismic events that go beyond devastation. It's about mysterious earthquakes that left behind questions science still hasn't answered. Unexplained seismic events that defy our understanding of the Earth's crust. Tremors that didn't follow the rules. Ground ruptures that appeared where no faults were known to exist. And cities that vanished, swallowed by the ground, without a logical cause. Most of us think of earthquakes as just natural disasters caused by tectonic plates grinding past each other. But sometimes, these geological monsters seem to break all the rules. How can an earthquake strike in the middle of a tectonically stable region? Why do strange lights appear in the sky before certain quakes? And what do ancient civilizations know about the Earth's shaking that we might have forgotten? Today, we're diving deep into the most powerful and mysterious earthquakes ever recorded. You'll hear about the deadliest seismic events in history, and the bizarre anomalies that came with them. You'll discover rare earthquake phenomena, like cities that shook even though they sat far from any known fault lines. You'll hear about strange electromagnetic pulses before major quakes, animals fleeing hours before disaster, and locations where science still struggles to explain why the Earth moved at all. These aren't just isolated incidents. Across the globe, patterns are emerging that suggest we still don't fully understand how and why the Earth shakes. In some cases, modern science has been left stunned, unable to explain the force, the frequency, or the fallout of certain quakes. Whether it's massive undersea shocks that trigger global tsunamis, or low-magnitude tremors in areas thought to be geologically silent, these events raise new questions about what really causes earthquakes and how well we can predict them. In the next few chapters, we'll explore some of the most devastating and inexplicable earthquake events from Chile to China, from the deep Pacific to Antarctica. We'll examine seismic data, survivor stories, unexplained earthquake anomalies, and the controversial theories that challenge mainstream geology. If you thought you knew how earthquakes worked, this video will shake that belief to its core. Stay tuned, because what you're about to hear may change the way you see the very ground beneath your feet. Earthquakes that shook the world. When the ground roared louder than history. There are moments in human history when the Earth didn't just tremble, it howled. These weren't your typical tremors or mild ground shivers. These were megathrust earthquakes. Massive, violent, earth-altering events that unleashed unimaginable energy, reshaped entire coastlines, and echoed around the planet for days. These were the largest earthquakes ever recorded, so powerful they didn't just shake cities, they rattled the very science we rely on to understand our world. The Richter scale, created in the 1930s, was originally designed to measure local earthquakes in California. It quickly became the global standard, but even that scale struggles to convey the sheer energy released by the world's biggest quakes. Seismologists now use the moment magnitude scale for accuracy, and when that scale reads above 9.0, we enter the realm of true seismic monsters. One of those monsters struck Chile in 1960. Known as the Great Chilean Earthquake, it remains the most powerful earthquake ever recorded in human history. On May 22, 1960, at precisely 3:11 p.m., the Earth ruptured off the coast of south-central Chile with a moment magnitude of 9.5. The rupture zone stretched over 1,000 kilometers, and the quake lasted an estimated 10 minutes, an eternity in seismic terms. What followed was widespread destruction. Entire towns were reduced to rubble, and over 2 million people were left homeless. But the shaking was just the beginning. This earthquake triggered a massive tsunami that rippled across the Pacific Ocean. In Hawaii, waves over 10 meters high struck without mercy. In Japan, thousands of miles from the epicenter, 138 people lost their lives to the wave generated off the Chilean coast. Even in the Philippines, the tsunami was felt. The global impact was staggering. More than 1,600 people were confirmed dead in Chile, though the true toll may never be known. And beneath the devastation, scientists discovered something odd. Parts of the South American continent had permanently shifted westward by more than 3 meters. It was one of the clearest examples of large-scale tectonic plate shift ever observed. Fast forward to December 26, 2004. It was the day after Christmas, and millions of people across Southeast Asia were celebrating with family. Then, at 7:58 a.m. local time, the Earth tore open beneath the Indian Ocean. The magnitude 9.1 to 9.3 earthquake struck off the west coast of northern Sumatra, Indonesia. It was one of the deadliest earthquakes in recorded history, and not just because of the shaking. This was a megathrust event where the Indian plate was subducting beneath the Burma plate. The rupture zone extended over 1,300 kilometers, one of the longest ever recorded. But it was the tsunami that followed that truly shook the world. In less than 3 hours, massive waves reached the coasts of Thailand, India, Sri Lanka, and eventually, even the east coast of Africa. The death toll was catastrophic. Over 230,000 people died in 14 different countries. Entire villages were wiped off the map. In some coastal areas, the ocean receded for miles before returning with deadly force. It was one of the worst natural disasters in modern history. In the aftermath, scientists were once again left piecing together data from an event so vast, it altered the rotation of the Earth. NASA reported that the earthquake had shifted the planet's axis by about 2.7 centimeters and shortened the length of a day by microseconds. These aren't just geological facts, they're planetary-scale anomalies. They challenge our assumptions about how the Earth behaves after such colossal releases of energy. Some researchers noted unusual gravitational field changes, and satellite images confirmed vertical shifts in the seafloor by several meters. Less than a decade later, on March 11, 2011, Japan faced its darkest hour. The 2011 Tōhoku earthquake was a magnitude 9.1 event that struck off the northeastern coast of Honshu, Japan's main island. It lasted 6 terrifying minutes and unleashed a tsunami that traveled up to 10 kilometers inland in some places. Over 20,000 people died, many of them swept away by the ocean that came roaring across fields, highways, and cities. Cars, trains, and even entire buildings were dragged into the sea. But the real nightmare began when the tsunami overwhelmed the Fukushima Daiichi nuclear power plant. The plant's cooling systems failed, triggering a triple nuclear meltdown and releasing radioactive materials into the atmosphere and Pacific Ocean. The disaster is considered the worst nuclear accident since Chernobyl. What made the 2011 Tōhoku event even more puzzling were the seismic patterns surrounding it. The area had experienced frequent moderate quakes for decades, but scientists didn't expect a rupture of this magnitude. The trench was considered locked, but the amount of energy released suggested it had been storing tension for far longer than predicted. Some geologists now believe the entire segment of the Japan Trench may be capable of producing even larger earthquakes in the future. There were also strange electromagnetic pulses detected in the ionosphere days before the quake. GPS satellites picked up fluctuations in the Earth's magnetic field near Japan. Some theorists claim this is evidence of a coming breakthrough in earthquake prediction, while others warn it could just be coincidental noise. But one thing is certain. The data doesn't lie, and the Earth was behaving unusually. In each of these catastrophic events, the Chilean megathrust, the Indian Ocean disaster, and the Tōhoku quake, the magnitude alone placed them in the record books. But the anomalies surrounding them raised even more questions. Why do some areas produce massive earthquakes centuries apart, while others, equally tense, remain silent for millennia? What hidden forces govern the release of tectonic stress? And could our current models of plate tectonics be missing something crucial? These largest earthquakes ever recorded remind us that beneath our feet lies a restless, dynamic planet. The ground may seem solid, but it floats on molten rock and shifting plates that have shaped the continents for billions of years. These megathrust earthquakes aren't just violent reminders of nature's power, they are windows into the Earth's deepest mysteries. And when these massive ruptures occur, they don't just devastate, they confuse, surprise, and often defy what we think we know about geology. In the coming chapters, we'll move from raw power to unexplainable oddities, from known fault lines to locations where earthquakes shouldn't exist at all. Because the more we dig into the Earth's past, the more we realize, it doesn't always follow the rules. Unexplained earthquakes that defy science. The tremors that challenge everything we know. Not all earthquakes make sense. Some defy the laws of geology as we know them. They strike without warning, in places geologists never expected, or exhibit behavior that leaves even seasoned seismologists scratching their heads. These are not your textbook tectonic events. These are the earthquakes with no explanation. Their patterns are strange. Their origins mysterious. And their aftereffects, in many cases, continue to baffle the scientific community decades or even centuries later. One of the earliest and most puzzling examples of strange seismic activity occurred in the heart of the United States, in a region far from any known tectonic boundary. The New Madrid earthquakes of 1811 and 1812 are among the most powerful quakes to strike the continental United States, yet they happened in what should be a stable zone. Between December 1811 and February 1812, a series of 3 massive earthquakes rocked the Mississippi Valley. The strongest is estimated to have reached a magnitude of 7.7. That may not seem extreme compared to the megathrust earthquakes near subduction zones, but considering the region's geology, it was astonishing. The shaking was so intense that it reportedly rang church bells in Boston, over 1,000 miles away. The Mississippi River flowed backward temporarily, forming temporary waterfalls. Entire forests sank into the ground, and strange mists and lights were reported rising from the earth. The earthquakes didn't just shake the land, they created permanent scars. Massive sand blows, subsidence zones, and sunken lands remain visible even today. But what makes the New Madrid earthquakes so mysterious is the lack of a clear tectonic cause. The region lies in the middle of the North American plate, far from any plate boundary. There's no major fault line visible at the surface. Some believe an ancient, buried fault zone deep within the crust may be responsible, but its reactivation remains unexplained. Others have speculated about isostatic rebound, glacial effects, or even deeper mantle processes. To this day, the New Madrid seismic zone remains one of the most poorly understood and potentially dangerous seismic regions in the world. Nearly 2 centuries later, another unexplained earthquake rocked China, one that stirred not only the earth but also a controversial scientific debate. On May 12, 2008, the Sichuan province was devastated by a magnitude 7.9 earthquake. Over 87,000 people lost their lives, and millions more were displaced. The destruction was immense. Whole towns collapsed. Infrastructure was destroyed. But one detail in particular made this earthquake stand out: the proximity of the epicenter to the Zipingpu Dam. Some geologists suggested that the weight of the water reservoir created by the dam may have triggered the quake by increasing pressure on an already stressed fault. This phenomenon, known as reservoir-induced seismicity, is rare but not unheard of. However, the magnitude and devastation of the Sichuan event made this possibility more alarming. If a dam could influence a fault to this extent, the implications for infrastructure projects near seismic zones would be enormous. To this day, no consensus has been reached. Some researchers insist the fault was already primed to slip, and the dam may have only played a small role, if any. Others believe human intervention may have tipped the balance. The Chinese government has denied any direct link, and studies remain inconclusive. What's certain is that this earthquake raised critical questions about how human activity might interact with hidden geological forces in unexpected ways. Just over 3 decades before Sichuan, another Chinese earthquake shook both the ground and the confidence in early warning systems. The 1976 Tangshan earthquake remains one of the deadliest in recorded history, killing an estimated 242,000 people. What makes Tangshan so mysterious isn't just the magnitude, 7.6, but the fact that it struck without warning in a region considered relatively low risk. Unlike other major quakes, there was no visible surface rupture. The fault that slipped was almost invisible, buried beneath decades of assumptions. Some seismologists had issued warnings of increased seismic activity in northern China in the months prior, but their alerts were ignored or downplayed by authorities. What followed was one of the greatest human tragedies of the 20th century. Survivors described lights in the sky, pets behaving erratically, and strange sounds emanating from the ground in the hours before the quake. But none of it was taken seriously at the time. Tangshan remains a grim reminder of how little we sometimes understand about the forces beneath us. These cases highlight a larger problem in the science of seismology. Earthquakes don't always follow the patterns we expect. Aftershock sequences, foreshocks, and energy distributions vary wildly even between similar fault types. In some cases, the aftershocks are more damaging than the main quake. In others, the Earth seems to settle quickly. Scientists still debate why this happens. Adding to the mystery are the reports of electromagnetic pulses detected before certain major earthquakes. In Japan, Italy, and even California, researchers have noticed changes in the ionosphere, increased radon gas emissions, and fluctuations in magnetic fields prior to seismic events. In one study, satellite data showed that electrons in the upper atmosphere spiked days before the 2011 Tōhoku earthquake. Were these just coincidences, or are they potential indicators of deeper processes at work? The evidence is still inconclusive, but the possibility is enough to keep researchers watching the skies as well as the ground. Then there are the earthquake lights, strange flashes or glows seen in the sky before, during, or after some quakes. These aren't urban legends. They've been documented in modern footage from Chile, Turkey, and Japan. One theory suggests they result from piezoelectric effects, electrical charges produced by rocks under intense stress, but no model fully explains their irregular appearance. These lights continue to baffle scientists and inspire both curiosity and fear in eyewitnesses. Animals also behave strangely before some earthquakes. Dogs barking without reason, birds fleeing forests, and deep-sea creatures surfacing hours before a quake are all phenomena that have been observed time and again. But science has yet to explain how or why. Do animals sense ground vibrations that instruments miss? Are they responding to shifts in electromagnetic fields or even sounds outside the human hearing range? Whatever the cause, animal behavior remains one of the most puzzling earthquake precursors we have. These earthquake mysteries point to a sobering conclusion. For all our technology, modeling, and measurement, the Earth remains one of the last truly unpredictable forces in our lives. Despite decades of research, we still cannot reliably forecast when and where the next big one will hit. And worse, we often fail to understand what's really happening when it does. Strange seismic activity, odd earthquake behavior, unexplained tremors, these are not the exceptions. They're part of a growing pattern that suggests we may be missing something fundamental about how our planet moves. In the next chapter, we'll take this mystery a step further and look at earthquakes that struck in places where they shouldn't have happened at all. Because sometimes, the Earth doesn't just break the rules, it rewrites them completely. Earthquakes in places they shouldn't happen. When the Earth moves without warning or reason. We expect earthquakes to happen in places like Japan, Chile, or Indonesia, regions perched along major fault lines where tectonic plates grind, slide, and collide. But what truly unnerves scientists and citizens alike are the earthquakes that strike in places considered geologically safe. These are the rare earthquakes that challenge the foundation of seismic science itself. From ancient bedrock to densely populated cities far from active faults, these tremors are rewriting the rules of where, when, and why the Earth shakes. One such shock came without warning on August 23, 2011, in the heart of the eastern United States. At 1:51 p.m. local time, a magnitude 5.8 earthquake struck near Mineral, Virginia. It wasn't the strongest quake in global terms, but its location made it extraordinary. The eastern US is far from any tectonic plate boundary, and the bedrock in this region is ancient and relatively stable. Yet in seconds, the shaking radiated through the ground like ripples in a pond, reaching as far north as Canada and as far south as Georgia. What made this event so unsettling wasn't just the unexpected location, it was the impact. In Washington, D.C., more than 130 kilometers from the epicenter, the Washington Monument cracked, and the National Cathedral sustained serious damage. Office buildings were evacuated across multiple states, cell phone networks jammed, and millions of people were left wondering what had just happened. The U.S. Geological Survey confirmed the quake originated from an old fault zone buried deep beneath the Appalachian Mountains, but even they admitted that very little is known about the region's seismic potential. Because the bedrock on the east coast is older and colder than in the west, seismic waves travel much farther. That's why a relatively moderate earthquake like the Virginia event could be felt by nearly one-third of the US population. But despite the data, questions remain. What reactivated this ancient fault? Why now? Across the Atlantic, another rare earthquake made headlines in 2002, this time in Manchester, England. Known more for its football clubs and industrial past than seismic risk, the United Kingdom is one of the least seismically active countries in the world. Yet in October of that year, the ground shook with surprising force. The quake registered only 3.9 on the Richter scale but was widely felt and left residents rattled. Seismologists attributed the quake to intraplate fault lines, fractures within a single tectonic plate rather than between two. These intraplate earthquakes are still poorly understood. Unlike plate boundary quakes, which are caused by the relative movement of two plates, intraplate quakes stem from stress accumulating within a single plate over long periods. The UK has dozens of small fault lines that are remnants of ancient tectonic collisions, and every so often, one of these faults slips. The Manchester event raised eyebrows because it wasn't isolated. Over the following months, several small tremors were recorded in the region, suggesting a swarm-like pattern. Yet the area had no prior record of significant seismic activity. The lack of a clear fault line, the swarm behavior, and the inability to predict the event all contributed to a sense of scientific unease. If earthquakes can strike in Manchester, where else might we be vulnerable without knowing? But the most controversial examples of earthquakes in unexpected places come not from ancient faults, but from human hands. In Oklahoma, during the 2010s, a dramatic surge in earthquake activity transformed the state into one of the most seismically active regions in the United States. For decades, Oklahoma averaged just 1 or 2 earthquakes of magnitude 3.0 or greater each year. By 2015, that number had exploded to over 900. This wasn't a coincidence. Scientists began to connect the dots between the rising earthquake frequency and the rise of hydraulic fracturing, or fracking, along with the disposal of wastewater into deep underground injection wells. The process involves injecting millions of gallons of pressurized water, sand, and chemicals into the ground to extract oil and gas. But the leftover wastewater is often re-injected into deeper rock formations, and it's this re-injection that appears to be the culprit. As the pressure builds in fault zones previously thought dormant, the stress can trigger slip events, what we now call induced earthquakes. One of the largest induced earthquakes in U.S. history occurred in Pawnee, Oklahoma, in 2016, with a magnitude of 5.8. It damaged dozens of buildings and reignited a fierce debate about whether industrial practices were responsible. The scientific community responded with increased monitoring and analysis. Studies found strong correlations between injection well volume and earthquake frequency. Yet even now, the line between natural and induced seismicity remains blurred. Not all injection wells cause quakes, and not all quakes near injection wells can be definitively linked. Some geologists argue that the pressure merely triggers earthquakes that would have occurred eventually. Others warn that human activity is awakening faults that were previously dormant and unpredictable. This debate isn't limited to Oklahoma. Similar concerns have emerged in Texas, Ohio, and even parts of Canada. In some regions, regulators have imposed restrictions on injection volumes or shut down specific wells. But the damage may already be done. Once a fault is reactivated, it's difficult, if not impossible, to put it back to sleep. The rise of these induced earthquakes raises broader questions about how we classify seismic events. Traditionally, earthquakes have been understood as natural phenomena, driven by tectonic forces deep beneath the Earth. But what happens when human activities begin to alter those forces? Are these still natural disasters, or are they the unintended consequences of modern industry? Classifying these events isn't just a matter of scientific accuracy, it has legal and ethical implications too. Who is responsible when a man-made earthquake causes damage to property or loss of life? How should building codes and insurance policies adapt in areas newly at risk? These rare earthquakes in unusual places expose the limitations of our current understanding. They challenge the idea that only plate boundaries are dangerous and reveal a deeper complexity beneath our cities, towns, and industries. Whether triggered by ancient faults, hidden weaknesses, or human intervention, these intraplate earthquakes remind us that the Earth has secrets we've yet to uncover. And while some of these tremors may seem minor compared to the world's largest quakes, their unpredictability makes them just as dangerous. In the next section, we'll explore the cutting-edge science and controversial theories attempting to make sense of these seismic mysteries, from electromagnetic pulses to gravitational shifts, and even the whispers of conspiracy. Because sometimes, the Earth's movements hint at forces far stranger than we've imagined. Scientific anomalies and controversial theories. When earthquakes hint at forces we don't understand, as science continues to refine its understanding of earthquakes, how they begin, how they spread, and why they hit certain areas, some events and patterns still remain outside the boundaries of conventional explanation. For decades, researchers have observed strange phenomena before and after seismic events. These include sudden electromagnetic surges, gravitational shifts, atmospheric anomalies, unusual animal behavior, and even mysterious lights in the sky. While mainstream science often urges caution in connecting these phenomena to earthquake predictions, the patterns are too frequent, too consistent, and too global to ignore completely. One of the most compelling fields of inquiry is the role of electromagnetic precursors. In the days and hours before several major earthquakes, instruments have detected spikes in low-frequency electromagnetic activity. These changes are sometimes measured in the ground, other times in the atmosphere, and occasionally even from space. Satellite data collected before the 2011 Tōhoku earthquake in Japan, for example, revealed a significant fluctuation in the ionosphere over the epicentral region. Similar findings were reported before the 2004 Indian Ocean earthquake and the 2008 Sichuan earthquake in China. The proposed mechanism is based on the idea that as tectonic plates grind against each other and stress builds along a fault, rocks in the Earth's crust generate tiny electric currents through a process called piezoelectricity. These currents can then cause localized changes in the surrounding electromagnetic field. Though intriguing, these anomalies are not always consistent or strong enough to provide a reliable method for earthquake prediction. Still, growing interest in this field suggests that future earthquake forecasting may not rely solely on seismic waves but also on signals emitted silently from stressed crust. Adding to the mystery are gravitational anomalies recorded during or after massive earthquakes. In both Chile in 2010 and Japan in 2011, researchers observed subtle yet measurable shifts in the Earth's gravitational field. These were not caused by the tremors themselves, but by the redistribution of mass following the tectonic movement. Earthquakes of high magnitude can physically shift the planet's mass, altering its rotation and gravitational signature. After the Chile earthquake, NASA calculated that the Earth's axis shifted by 8 centimeters and shortened the day by 1.26 microseconds. Japan's quake reportedly had a similar effect. These gravitational changes are now detectable with satellite-based instruments such as the GRACE, Gravity Recovery and Climate Experiment, mission, which maps variations in Earth's gravity. While these measurements occur post-quake, some researchers speculate that gravitational fluctuations prior to the event might act as an early warning. It's still a developing theory, but if validated, it could add another layer to future earthquake predictions. Earthquake lights and clouds are another set of phenomena that have puzzled observers for centuries. Documented as far back as the ancient Greeks, earthquake lights are sudden flashes or glows that appear in the sky shortly before or during seismic activity. These lights have been filmed in recent decades in places like Japan, Mexico, Italy, and Turkey. Some appear as glowing orbs, others as streaks of light or flashes like lightning. The cause remains unknown. One theory suggests that when certain rocks are compressed, they release electrical charges that ionize the air, creating visible light. But this has yet to be conclusively proven in laboratory conditions. Similarly, there are reports of unusual cloud formations, often described as vertical, pillar-shaped clouds or sudden, isolated banks of mist, seen above future epicenters. While meteorologists caution that these clouds could be coincidental, their appearance has become part of the folklore surrounding earthquake precursors. To skeptics, these stories are anecdotes. To open-minded scientists, they represent patterns worth investigating further. Another phenomenon that consistently appears before major earthquakes is animal behavior. There are countless documented cases of dogs barking frantically, cats hiding for no reason, fish beaching themselves, and birds abandoning their nests just hours before a quake. In 1975, officials in Haicheng, China, noticed strange animal movements and evacuated the city. Days later, a 7.3 magnitude earthquake hit. Thousands of lives were saved. Despite this, the scientific community remains cautious. While animals may indeed sense vibrations or electromagnetic signals that humans cannot, this behavior has proven too inconsistent to use as a standalone prediction method. Where mainstream science steps back, controversial theories begin to fill the void. One of the most debated is the idea that earthquakes can be influenced or even triggered by man-made technologies such as HAARP, the High-Frequency Active Auroral Research Program. Located in Alaska and originally funded by the US Air Force and Navy, HAARP was designed to study the ionosphere. But conspiracy theorists have long believed the facility could manipulate weather or generate seismic events by directing high-frequency radio waves into the atmosphere. According to the HAARP earthquake theory, injecting massive amounts of energy into the ionosphere could, in theory, destabilize tectonic stress zones. Some theorists link HAARP to specific earthquakes, including the 2010 Haiti disaster and even the Japan earthquake in 2011. However, there is no credible scientific evidence supporting these claims. The frequencies used by HAARP are not strong enough to influence geological processes miles beneath the Earth's surface. Still, the theory persists, in part because so many earthquake anomalies remain unexplained. Beyond human technology, some scientists are exploring the deeper interactions between the Earth's core, its magnetic field, and seismic activity. The Earth's liquid outer core generates a powerful magnetic field through a process called the geodynamo. This field is not static. It fluctuates, reverses, and occasionally weakens. Some researchers believe changes in the magnetic field may correlate with increased seismic activity, although the relationship is far from clear. A weakening magnetic field could alter the balance of forces deep within the Earth, perhaps influencing the stability of tectonic plates. Other researchers speculate that interactions between the core and mantle could create hotspots of stress that eventually trigger earthquakes. While much of this remains theoretical, it opens a new dimension to earthquake science, one that stretches beyond fault lines and into the hidden depths of our planet. In the end, science thrives on questions. And when it comes to earthquakes, we have more questions than answers. From electromagnetic pulses to gravity shifts, from glowing skies to panicked animals, the signs are there. Whether they form a coherent picture or are just fragments of unrelated events remains to be seen. What's clear is that the Earth doesn't always give us the answers we want. Sometimes, it only hints at truths we're not yet ready to understand. As we move deeper into this mystery, we'll shift our focus to the past. Some of the most puzzling and devastating earthquakes in history were recorded not in datasheets but in ancient texts and ruins. These lost seismic events may hold clues to what's coming, and whether our ancestors knew more about the Earth's behavior than we realize. Ancient and historical earthquake records when the Earth shook before science could explain it. Long before the invention of seismographs and satellite imaging, the ground still shook. And when it did, ancient civilizations responded not with data, but with stories. These weren't just simple tales. They were vivid accounts, deeply embedded in religious texts, mythology, and oral traditions, fragments of knowledge passed down through generations. Today, these records offer more than just cultural insights. They hint at ancient earthquake mysteries, seismic disasters that shaped civilizations, and events that still raise questions in the modern scientific world. In ancient China, scholars recorded natural events with remarkable precision. Historical texts like the Book of Han and the Book of Later Han mention ground shaking, splitting earth, and sky phenomena associated with disasters. In 1831 BCE, Chinese records describe the earth trembling while red clouds covered the sky and animals fled in terror. Some of these texts reference luminous lights appearing in the sky before the ground began to convulse, an observation that mirrors modern reports of earthquake lights. Without the framework of modern geology, these accounts often attributed the shaking to the wrath of heaven, but the level of detail suggests first-hand observations of true seismic events. Mesopotamian tablets also speak of quakes, linking them to celestial omens. The Sumerians, among the world's earliest civilizations, believed that the gods controlled the earth and that their anger was expressed through tremors. One Akkadian text describes the ground shaking so violently that the heavens cried out and buildings crumbled into dust. These writings may seem symbolic, but they correlate with a region known for fault lines beneath the Tigris and Euphrates valleys. While science has filled many gaps left by mythology, these ancient narratives still pose questions. Were these just allegorical interpretations, or did ancient civilizations witness and record earthquake phenomena we've yet to fully understand? In Mesoamerica, the Maya and Aztecs had complex mythologies surrounding the destruction and rebirth of the world. Many of their stories involve earthquakes as divine judgments. The Aztecs believed that the current world, the fifth sun, would end in a massive earthquake. Whether metaphor or memory, this belief could have been inspired by seismic events long forgotten by modern history. In Guatemala and southern Mexico, tectonic activity along the Middle America Trench has historically caused powerful quakes. Some researchers believe that repeated exposure to these disasters influenced cultural mythology that treated earthquakes as cyclical and apocalyptic. Among the most compelling ancient earthquake mysteries is the lost Greek city of Helike. Situated on the coast of the Peloponnese, Helike was a prosperous city during the classical period. But in the winter of 373 BCE, the earth beneath Helike gave way. Ancient writers including Strabo, Diodorus, and Pausanias described how an earthquake struck at night, followed by a massive tsunami that swallowed the city and its population. Within hours, Helike had disappeared beneath the sea. For centuries, the city was believed to be a legend, until modern archaeologists discovered its ruins buried beneath layers of sediment. What stunned researchers was not just the scale of destruction, but how accurately the ancient texts described the event. The earthquake and tsunami were so sudden and powerful that they erased a city in a single night. This event is now studied not only as a historical earthquake but also as a warning. The Helike disaster shows how coastal settlements in seismically active areas are vulnerable to combined earthquake-tsunami events, much like what occurred in Japan in 2011. It also illustrates how ancient cultures witnessed and preserved real geophysical data in the form of myth and memory. Another historical earthquake that stands out is the Crete earthquake of 365 AD. Striking during the height of the Roman Empire, it caused a massive tsunami that devastated the eastern Mediterranean. In Alexandria, Egypt, thousands perished as the sea surged several kilometers inland. Ancient sources describe ships being carried over city walls, temples collapsing, and widespread panic. The magnitude is estimated to have been around 8.5 or greater, centered near the Hellenic Arc subduction zone. What's striking about the 365 AD event is not only the scale but the reach of the tsunami it generated. Historical records from Libya, Greece, Sicily, and the Levant describe a simultaneous disaster. Modern geological studies have confirmed a massive uplift in western Crete, up to 10 meters in some areas, matching the ancient descriptions of harbors vanishing overnight. These historical earthquakes are not just tales from the past. They provide clues to seismic patterns that could repeat in our future, especially as coastal cities continue to grow along known fault lines. Indigenous cultures across the world also provide accounts of ground shaking that predate colonization. In the Pacific Northwest of North America, the oral traditions of the Maka, Nuu-chah-nulth, and other coastal tribes tell of a night when the ground shook violently and the ocean swallowed the land. For generations, these were treated as creation stories or myth. But geological studies have now confirmed that a massive earthquake struck the Cascadia subduction zone around the year 1700, sending a tsunami across the Pacific and even reaching Japan, where it was recorded as an orphan tsunami with no apparent cause. The convergence of indigenous memory and scientific data has reshaped how researchers view oral histories. These are not just symbolic legends. They are accurate, community-preserved memories of natural disasters. Similar stories exist in New Zealand, the Andes, and parts of Southeast Asia, each one reinforcing the idea that the Earth's violent movements have been witnessed and remembered long before modern instruments could measure them. These ancient and historical earthquake records challenge the notion that our understanding of seismic activity began in the scientific era. Instead, they suggest a long human tradition of observation and memory, often recorded in poetic or mythical language. The fact that many of these records describe sky phenomena, sudden water displacement, unusual animal behavior, and destruction beyond imagination suggests that ancient peoples may have documented earthquake effects we still can't fully explain. Were they seeing things we dismiss today? Did they have a deeper awareness of the signs leading up to major seismic events? And are we overlooking clues buried in mythology and oral tradition that could help us better prepare for the next big one? As we continue to explore these lost cities, mysterious tremors, and ancient earthquake stories, the line between science and storytelling becomes increasingly blurred. The past may not only hold forgotten disasters, it might also contain knowledge that can protect us in the future. In the next section, we turn our attention forward. Because while history gives us context, the present reveals our limits. Earthquakes remain one of the least predictable and most dangerous forces on Earth. Earthquakes in the future, what we still don't know. The coming quakes and the limits of modern science. For all the advances in technology, modeling, and data analysis, earthquake prediction remains one of the most elusive goals in Earth science. We can forecast weather, track hurricanes, and even anticipate solar storms, but predicting the exact time, location, and strength of an earthquake is still beyond our reach. Despite decades of research and billions invested in monitoring networks, the Earth continues to surprise us. Scientists can estimate probabilities based on historical data and tectonic activity. They can tell us that a fault is locked, that pressure is building, and that a rupture is likely within a certain number of years. But these are forecasts, not predictions. There is no seismic equivalent of a hurricane warning. No sirens that can give people hours, or even minutes, of notice. Earthquake prediction remains the holy grail of seismology, and the deeper we dig into fault systems, the more complex they appear. One reason prediction is so difficult is the chaotic nature of fault behavior. No two earthquakes are exactly alike, even when they occur along the same fault. The way stress builds and releases along fault lines depends on a dizzying number of factors: rock composition, fluid pressure, fault geometry, and more. A fault may go quiet for centuries, then rupture without warning, while another may creep slowly over decades without producing a major quake. This inconsistency makes reliable earthquake forecasting extremely difficult. Yet, despite the unpredictability, we know that certain areas are dangerously overdue. Along the Cascadia subduction zone off the Pacific Northwest coast of North America, pressure has been building for centuries. This fault is capable of producing a magnitude 9 or greater quake, similar in size to the one that devastated Japan in 2011. Geological evidence shows that the last major rupture occurred in the year 1700, and it triggered a massive tsunami that reached Japan hours later. Experts believe another event of similar magnitude is inevitable. The only question is when. In Istanbul, Turkey, the North Anatolian Fault runs just south of the city. Over the past century, a series of powerful earthquakes has been migrating westward along this fault. Seismologists now believe that Istanbul is next in line. With over 15 million people living near this active fault, the implications of a future megaquake are staggering. Structural vulnerabilities, high population density, and limited preparedness could lead to catastrophic consequences. Tokyo, sitting atop a complex junction of tectonic plates, is also at risk. Japan experiences more earthquakes than almost any other country, but Tokyo hasn't seen a major direct hit since 1923, when the Great Kanto earthquake killed over 140,000 people. The city has invested heavily in earthquake-resistant infrastructure, but experts warn that even the best engineering may not withstand the next big one. And just like Cascadia and Istanbul, it's not a question of if, it's when. These seismic gaps, where stress continues to accumulate silently over long periods, are among the most worrisome features in global earthquake forecasting. They represent zones where we expect major ruptures, but where little or no activity has occurred in decades or even centuries. The longer the quiet, the greater the tension, and the more destructive the eventual quake may be. But because we can't see stress directly, we rely on indirect measurements, which are often incomplete. Complicating matters further are so-called silent earthquakes. Unlike traditional quakes, these events release energy slowly over days or weeks, without generating strong shaking. They were first identified in Japan in the 1990s and have since been observed in several subduction zones around the world. These silent quakes don't cause immediate destruction, but they may influence larger seismic events by redistributing stress in unpredictable ways. Their discovery has added a new layer of complexity to our understanding of fault mechanics. The future of earthquake forecasting may lie not in human observation alone but in artificial intelligence. Machine learning algorithms are now being trained on massive seismic datasets, searching for subtle patterns that human analysts might miss. These AI models can sift through years of ground motion data, satellite imagery, electromagnetic signals, and geological measurements to identify early warning signs. One promising avenue is the use of neural networks to detect anomalies in real time. By feeding AI systems with continuous seismic and geophysical input, scientists hope to create systems that can recognize the unique fingerprint of a fault preparing to rupture. Some preliminary results have been encouraging, with AI detecting low-frequency tremors that preceded larger quakes by days. But the challenge is scaling these models globally and ensuring they work across different geological environments. There's also potential in combining AI with other forms of data, like changes in animal behavior, shifts in the magnetic field, or even atmospheric anomalies. The dream is a multi-layered earthquake prediction system that integrates everything from subsurface strain measurements to cloud formation. But getting there will take years of refinement and validation. Earthquake prediction is not just a scientific puzzle. It's a problem of complexity, uncertainty, and limited visibility into the planet's most inaccessible zones. Even if we could achieve accurate short-term forecasting, there are still massive logistical and social challenges. How do you evacuate a city of millions with only hours of notice? How do you avoid false alarms that could lead to panic or economic disruption? And how do you maintain public trust when dealing with a phenomenon so inherently unpredictable? One thing is certain, the stakes are rising. As global populations concentrate in megacities near major fault lines, the potential impact of future megaquakes becomes even more severe. Urban centers like Jakarta, Los Angeles, Tehran, Manila, and Kathmandu sit atop active seismic zones. Many of these cities are growing rapidly, with infrastructure that may not withstand the shaking that lies ahead. Earthquake forecasting must evolve, not only in accuracy but in the way it communicates risk. Communities need to be better prepared, buildings better designed, and emergency response systems more resilient. Predicting the exact moment of a quake may still be out of reach, but understanding where and how they're likely to strike is already saving lives. The next big earthquake may not be tomorrow or next year, but it is coming. Somewhere, deep below the surface, a fault is creeping toward its breaking point. Whether it happens in a quiet corner of the ocean or beneath a sprawling metropolis, the results will test the limits of our preparedness, our science, and our understanding of the planet we call home. In the next chapter, we'll shift from theory to raw reality. Because when the Earth breaks loose and cameras are rolling, we capture not just the destruction, but rare insights into how the ground truly moves. Some of these moments have redefined our understanding of seismic behavior and survival in ways no model ever could. Earthquakes caught on camera, shocking footage and what it reveals when the Earth shakes and the lens captures everything. In the digital age, earthquakes are no longer silent disasters. They're captured in real time, from multiple angles, by smartphones, security systems, drones, and dash cams. These moments, raw, terrifying, and unfiltered, are not just viral sensations. They're scientific gold. Watching earthquakes caught on camera has revealed things about ground motion, structural response, and human behavior that no simulation or textbook ever could. When the 2011 Tōhoku earthquake struck Japan, countless cameras were already running. Surveillance systems recorded the floors of supermarkets rippling like waves. Vehicles swayed violently in parking lots. Office buildings twisted as if made of rubber. Within minutes, social media was flooded with video clips showing ceilings collapsing, power lines swaying, and people scrambling for shelter. These weren't just shocking earthquake footage clips designed to go viral, they were real-time case studies. Engineers studying the footage learned how different types of buildings absorbed seismic waves, where structural weaknesses were most exposed, and how evacuation patterns affected survival rates. In Nepal, during the devastating 7.8 magnitude earthquake of 2015, handheld videos showed ancient temples crumbling into dust. One moment, a bustling square full of life and tradition. The next, complete chaos. What those videos revealed was how unreinforced masonry, a staple in many historic cities, stood no chance against lateral ground motion. Seeing bricks fall, beams snap, and crowds panic in real time forced planners and architects around the world to rethink how older structures in high-risk areas should be preserved or retrofitted. One of the most harrowing pieces of earthquake footage came from Turkey during the 2020 Elazig earthquake. A CCTV camera recorded a narrow alleyway just seconds before the quake hit. Pedestrians casually strolled, unaware of what was coming. Then, in a violent jolt, the ground shook, buildings lurched, and dust exploded into the frame. As chunks of concrete crashed to the pavement, people ran in all directions. The clip lasted only 30 seconds, but it captured more than destruction, it showed instinct. Freeze, flight, panic, protection. The full spectrum of human response compressed into a single terrifying moment. In Chile, a country well acquainted with seismic threats, videos from the 2010 magnitude 8.8 earthquake revealed another layer: resilience. Many high-rise buildings swayed dramatically but did not collapse. Why? Chile's strict building codes, enforced after previous quakes, had paid off. Watching those towers bend without breaking gave engineers a powerful case for flexible structures over rigid ones. The footage became part of structural engineering curriculums around the world. Beyond the concrete and steel, these videos also give us insight into behavioral patterns. In many clips, people instinctively run outdoors. While this is common, it's not always the safest response, especially in urban environments with falling debris. Earthquake survival stories caught on camera often show the benefit of ducking under sturdy furniture or staying in open spaces when possible. Some survivors later described the disorienting experience of time distortion, how a minute of shaking felt like an eternity, and how their bodies seemed to act before their minds could process what was happening. Animal behavior, too, has been captured in these moments. In a widely circulated video from Japan, a dog begins barking frantically and pacing in circles moments before the ground begins to move. In another clip from Mexico, birds flee the trees seconds before the quake is felt. While anecdotal, this kind of footage supports what many researchers have long suspected: animals may be sensitive to vibrations or signals that precede seismic events. These instinctual reactions, if better understood, could one day form part of a more holistic early warning system. Psychologists have also studied these recordings to understand how people behave under extreme stress. Some individuals immediately rush to help others. Others freeze or scream. In group settings, panic can spread quickly, but leadership, someone calmly directing others, often leads to better outcomes. Earthquake survival stories aren't just about where someone was standing or what building they were in. They're about decision-making in chaos, mental preparedness, and sometimes, pure instinct. These videos also show the secondary dangers earthquakes bring. Fires breaking out from ruptured gas lines. Water pouring from broken mains. Electrical sparks igniting flammable debris. And perhaps most importantly, the delayed response time. Many clips show that the first few seconds of a quake are deceptive, just mild shaking. But then the violent wave hits. It's during this lull that people make life-saving or life-threatening decisions. There is a growing movement to use this footage not only for scientific analysis but for public education. Real-life visuals speak louder than diagrams or drills. Watching shocking earthquake footage from across the globe teaches viewers what to expect, what to do, and what not to do. Governments and schools are now incorporating these clips into training modules, hoping that seeing the reality might prompt better preparedness. Despite their terrifying nature, these earthquake recordings offer hope. They show that well-built structures can survive, that trained instincts can save lives, that community resilience, clear communication, and preparation can turn disaster into survival. In a world where the ground can shift at any moment, these captured moments serve as warnings, lessons, and sometimes, miracles. As we head into the next section, we move from the global to the remote. Because even in the least expected corners of the world, places as silent as Antarctica, there are seismic surprises waiting to be uncovered. And in one such place, a powerful tremor struck where it should have been impossible, leaving researchers with more questions than answers. A jolt from the frozen silence. On August 12, 2021, deep beneath the icy expanse of Antarctica, the Earth trembled. A magnitude 6.1 earthquake struck near the South Shetland Islands, sending a ripple of confusion through the global seismological community. This was not just another tremor on a known fault line. It happened in one of the most tectonically quiet regions on the planet, an area historically known more for its glaciers than for its geological activity. The Antarctica earthquake caught many scientists off guard. While there are some minor faults scattered beneath the ice, the region lacks the kind of plate boundary tension seen in hotspots like the Pacific Ring of Fire. For a quake of this strength to emerge in such a frozen and supposedly stable environment raised questions that have yet to be fully answered. Initial theories focused on local fault zones beneath the Antarctic peninsula. But what really sparked interest was the growing suspicion that climate change may have played a role. As the polar ice continues to melt at record rates, the weight pressing down on the continent's crust is decreasing. This sudden loss of pressure, known as glacial isostatic rebound, can cause the Earth's crust to flex and shift. Over time, this movement may introduce new stresses to areas once thought to be geologically dormant. Some scientists now believe that as Antarctica's ice thins and retreats, it could reveal fault lines that have been locked and silent for thousands of years. The 2021 event may be one of the first signs of this shift. The quake was followed by a smaller but still significant aftershock, and GPS monitoring detected slight changes in elevation across the region, further suggesting tectonic involvement. What's particularly unsettling is how little we know about the seismic future of Antarctica. Most global monitoring systems are focused on more populated regions. In contrast, Antarctica remains largely uncharted in terms of deep Earth surveillance. With climate change accelerating, the interaction between melting ice and crustal stress could become a new frontier in seismic science. Ongoing research is now underway, including satellite imaging, ice-penetrating radar, and deep seismometer deployment. The 2021 Antarctica earthquake may be a warning shot, a subtle message from the planet's most isolated corner. It's a reminder that even the coldest, most remote regions are not immune to change, and that tectonic surprises can happen where we least expect them. For all the data we've gathered, all the equations we've written, and all the maps we've drawn, earthquakes continue to challenge our understanding. From the world's biggest earthquakes that shook entire continents to those mysterious tremors in places no one ever expected, these seismic events remind us that the Earth is still very much alive and unpredictable. Many of these disasters can be scientifically explained, but others remain wrapped in uncertainty. Earthquake mysteries, historical anomalies, and emerging seismic trends point to a truth we often overlook: our planet holds secrets we haven't yet uncovered. And sometimes, the ground moves in ways that defy all logic. If you've ever witnessed an earthquake or have a theory about what causes the unexplained ones, we'd love to hear from you. Share your experiences and thoughts in the comments below. And if you're fascinated by natural disasters explained, strange Earth facts, and seismic phenomena the world still doesn't fully understand, make sure to subscribe to the channel. There's so much more to explore beneath the surface.